Hello, multivariable calculus students. This is the last part of section 9.3, and this is going to be on projections. This particular topic, I didn't quite fully realize the impact that it has throughout our curriculum until after probably the second year I really taught it. This will carry out and show up again over and over and over again. And so it's really important stuff, and it's actually really interesting as well because it manipulates excuse me, it manipulates vectors in such a way that we're able to project a vector's motion as well as its magnitude onto another vector. And in our area of study, this is going to be really, really helpful for us. So right now, all you need to be able to figure out is a vector projection and a scalar projection. Now, I think that both terms, I think the notation, I think they're all of it's pretty confusing, and it's actually much simpler. And again, it took me a little while before I was able to teach it in such a way that I think helps understand how simple it can be. So what I'm going to do is I'm actually going to kind of go backwards in the notes. So right now the notes have a vector projection first and a scalar projection second. I'm actually going to teach it the opposite. I'm going to go with a scalar first, and there's a really main reason why. You're going to see this in a second. So if you jump down to the bottom, I'm going to walk you through where all of this comes from, and I think if you can really grasp this and understand it intuitively, you're going to remember it for much longer. These formulas are cumbersome, but I think if you understand what I'm about to teach you and why it works, then you're going to be able to not need to memorize the formulas. They'll just make some sense. Okay. So first off, what we're going to do is draw two different vectors, and we're going to label this one as B just so that it matches. It does not matter, by the way, but we're going to label that one B and this one A, and that's just simply so that it matches our formulas. Okay. What I'm also going to do is I'm going to take the vertical down from B here, and I'm going to mark a vector here that I'm going to call C, and that's just a complete dummy variable. You can call it whatever you want, but just so that we have something to name it, we're going to call that C. All right, the main idea here, just so that you have this in your mind, is that a scalar projection is simply just the magnitude of C. That's all it is. The vector projection is the vector C. That's all we're trying to figure out. Now, our current textbook, as well as many other textbooks that I've seen, I believe make it appear so much more complex than that. That's all it is. So we're gonna find out a formula for the magnitude of C, and that's called the scalar projection. And then we're going to find the formula for that actual vector, the components of that actual vector. That's the vector projection. Okay. Now here's what it is in the context of A and B. So what we have is a vector B, and we really want to have an idea of what type of impact B has on A. So B is off of A by an angle of theta. We want to know what is the horizontal or the component along A in which B affects A. And we want to know how does it affect it both in magnitude and in size. So we want to look at the vector components as well as the magnitude itself. We know the direction. The direction is going to be directly in the same course as A, but we want to know what's going on with the magnitude and the actual components of that particular vector. All right, we're going to start with the scalar projection. So with our scalar projection, we're going to use a trig identity. So we have cosine of theta, which is going to be equal to the adjacent side, which is the magnitude of C, divided by the magnitude of B. And what I'm going to do is solve for C, or the magnitude of C, excuse me, and we get the magnitude of B multiplied by the cosine of the angle theta. Now this may look a little bit familiar to you because when we had our, so let's see, this is our dot product formula. we had the dot product between two vectors, which is exactly what we have here. We have two vectors, A and B. They're connected at an initial point with an angle between. So the dot product is the magnitude of A multiplied by the magnitude of B multiplied by the cosine of our angle. So what we have missing in this little part to our equation here is simply just the magnitude of A. So what I want to do is divide by the magnitude of A in my dot product formula. So I'm going to take my dot product formula, just rewrite it slightly, and I get A dot B divided by the magnitude of A, which is equal to the magnitude of B times cosine of the angle. Now, if we compare what we have in this particular formula with this black equation that we have here, the right sides are identical. That means that the magnitude of C is simply A dot B divided by the magnitude of A. This is the scalar projection equation. That's all it is. That's where it comes from. That's the intuition behind it. Now, what is that in our picture? Well, remember, this value, and actually let me back up just 1 second. So when you think scalar, you should think a number. So this is going to give you a number. It's a numeric value. It's not a vector. It's not going to give you components. It's going to give you a single number. That number is the magnitude of this particular vector. That's the length of that side projected down from B. And if you go up to our formula in the notes, it's exactly the same. There it is, A dot B divided by the magnitude of A. Now they use this notation. This is common across many, many schools. So it's called the component. I don't know why they call it the scalar projection of the component other than, and I'll show you this in a second, the component of B. I'll explain that in a minute. I don't know why they use so many of the different terms, just to kind of confuse you, but this is the component of B onto A, and that is called the scalar projection, and that's your formula. Now, if you do think about this as a projection of B onto A, what we just found was the first component of B, and I think that's where that component comes from, but I think that it can be confusing for people because there's so many different terms that kind of mean the same thing. So if we were to look at B, like the vector B, that the thing we just found, the magnitude of B times the cosine of the angle, that is the let's just call it the horizontal component of B. Now the issue with these vectors is that these vectors can be turned and tilted whenever they want. I mean, they don't need to be horizontal and thought of as on the x-axis. They don't need to be that at all. We can rotate them whenever we feel like we need to. This setup right here is basically that B, the component here for B is simply just along A. So this portion of the components of B are representative of the magnitude along that vector A. Now, we don't really care about the vertical component because it doesn't have anything to do with A. So the whole idea here in terms of the component of B onto A is simply just the part of B that matters to A is being projected down to it. Okay, let's move on. I hope that made some sense. I wish I could, get a sense by just looking at you as a class, but my hope is that made some intuitive sense and you see where it comes from. Okay, we've tackled the magnitude of C, which is the scalar projection. Now what we're going to do is we're going to figure out with this blue vector, we're going to actually figure out what the true components are of that vector. Now, remember, the way I drew it, it appears as though A is along the x-axis, but that is often not the case. It's often not so nice. So it very well may be that the components of C, that you have something and then 0, which means it would be along the x-axis. Or the components could be much more complex. It could be in 3 dimensions. We're going to set up a formula that will identify the true components of C all we know right now is the magnitude of C. Now this part I think is really cool because you can overcomplicate it, and I'm not going to do that. I'm going to try to simplify it a great deal. Here's what we have, okay? So we have, I'm just kind of going to move this picture over for a minute. Here was A, and here is C, the projection of B onto A. Okay, we agree that they're on the same path here, right? So the vectors are essentially overlapping. The issue is that we want to figure out how long C is, and all we know about C is that the magnitude of C is equal to A dot B divided by the magnitude of A. That's what we just found out a second ago, okay? So we know that. Here's the easiest way I could possibly think of to explain this. What if we were to take A? Now, we don't know the magnitude of A. The magnitude of A could be 8, it could be 30, it could be 1. But what we're going to do is we're going to make A unit vector. Let's pretend just for a moment that that is 1 unit in length right there in green. So we're going to force A to be a unit vector. Now, how do we do that? Well, we learned this just a little bit ago in our beginning portion of the chapter. We take A and we simply divide by the magnitude of A. That gives us a vector that is in exactly the same path as A, but exactly 1 unit in length. Okay, so then if we want to figure out what's going on with C, why don't we take that unit vector that we just found, and why don't we just stretch it out to C? Well, how do we do that? We take the magnitude of C and we simply multiply it by that unit vector. If you remember, we did an example of this. It was actually in section 9.2. It was example 9, and I'm referencing it. I'm looking at it right now. It says, find a vector that has the same direction as the vector -2, 4, 2, but has a length of 6. And if you flip back in your notes, you can see that example. That's exactly what I'm proposing we do right here. I'm saying that what we want is a vector that is this vector C. We want a vector that's in exactly the same direction as A, but we want it to be as long as we know C is long. Therefore, we take A, make it a unit, and then multiply by the magnitude of C. And here's what we get. We get A dot B divided by the magnitude of A multiplied by the unit or the vector A as a unit vector. This is called the vector projection. And it's the vector projection of B onto A. And if you look up in our notes, you will see this is exactly how they write it. I almost always leave it just like this, because to me that makes way more sense. This is A as a unit vector, and this is the magnitude of C. And I made up C, we did that together, but that's how I think of it. I don't even bother with rewriting it as that denominator squared, because to me, that doesn't help me remember it. What helps me remember it is to think about it logically. And to me, it's very logical to take A and make it a unit and then just scale it to what I want it to be. So my hope here, after you've seen this, is that projections, which can be very confusing, my hope is that this analysis of it makes it feel a little bit more straightforward, and it also sticks with you a little bit longer, because we do use these quite often here as we continue, especially in chapter 13. Okay, we're going to move on to the next page and try some of those examples. All right, we're just going to do 2 examples, and then we'll be done with section 9.3. So the first example is that we're going to take a look at B and A, and we're going to look at the scalar projection and the vector projection if B is projected onto A. So we have our scalar projection first, which is the component of B onto A. And remember that formula is A dot B divided by the magnitude of A. And the dot product will give us -2 and 3 and 2 divided by the magnitude of A, which will be square root of 1 squared plus 1 squared. Oh, back up, sorry, I'm doing the magnitude of B. That's not going to be quite right. So we have -2 squared plus 3 squared plus 1 squared. So then this gives us 3 divided by, let's see, that's going to be 9 and 4 and 1, so the square root of 14. So that is the length of the projection. That's the scalar of the projection. Now what we're going to simply do is the vector projection of B onto A. And remember, we're using the thing we just found, A dot B over the magnitude of A. So the thing we just calculated. But then we're going to take A and make it a unit vector. So we have most of the calculations already. We know that the first part of that is 3 root 14 because we just calculated it. And A is -2, 3, and 1. However, we're going to multiply or divide by the magnitude, which we already calculated was the square root of 14. And so for our vector projection, what we get is, actually, you know what, I'll write it down here. So we get 3 divided by 14 multiplied by this vector, which I'm totally fine if you leave it like that. Or you can distribute it and get, let's see, -2 over 7 and 9 over 14 and 3 over 14. That's totally fine too. Sometimes we'll simplify more often than not. Sometimes we'll leave it outside. It just kind of depends on the problem. Okay, let's try example 12. So we have the scalar and vector projections. This wording is a mistake. I apologize. So we're going to project same thing, B onto A, and I'll make a change. Please change your notes. Otherwise, it's very confusing even to know exactly what it's asking because it's not using the right language. Okay, so we have our scalar projection, which is going to be A dot B divided by the magnitude of A. And that gives us, let's see, be careful here because remember B does not have an I component, so we have 0 there, and then -1 times 1, so -1, and then 4 times 1/2, so 2. And then we take the square root of A, we're doing the magnitude of A, so 2 squared plus -1 squared plus 4 squared. And that gives us 1 divided by, let's see, 16, 4, and 1. So we have square root of 21. So there's your magnitude. There's your scalar projection. And then your vector projection of B onto A will be the same thing that we just found, the magnitude of what we are looking at, multiplied by the unit vector of A. So we have 1 over the square root of 21 multiplied by, so A is going to be 2, -1, and 4. And we know the magnitude is the square root of 21. So we get 1 over 21 times the vector 2, -1, and 4, which is totally fine to leave it, or you can distribute it through. So we have 2 over 21 and -1 over 21 and 4 over 21. And there you go. That is section 9.3. And keep in mind, if you haven't already seen it, but we have answers here in the back of each section, so you can double check that kind of stuff. Check my work, check your own work. But congratulations, you've done the dot product. And now what we can do is move on to the cross product in section 9.4. Thank you.